class, I'm going to explain the details of context switch in Pintos operating system. This is an overview of the talk. We'll have 5 topics: process structure, process state, process context, and schedule, and switching the 2 thread. The first topic we are going to deal with is the structure thread or struct thread that represent a process. This is one of the most important data structure in operating system kernel. This is struct thread. It contains a various attribute that is required to represent a thread. The first one is thread ID, the status of the thread priority, and then it contains a pointer to the kernel stack, and I will explain it later. Then it contains a pointer that points to the page table it uses. There are 4 process states in Pintos operating system, that is running, ready, blocked, and that are 3 basic process state. And then there is another state called dying. This is the state where process stays after it calls exit and before the operating system completely removes all the data structure that has been allocated for the process. Most important function for a thread is creating a thread. This is the prototype of the thread in the bar create. It has 4 attributes: name and thread priority, and the function it wants to execute when the thread is called, and the parameter list that needs to be supplied to the function you want to execute. This is the details of creating a thread. Inside thread on the create, it calls a function called init thread. In memset, it allocates memory for the thread structure and set it to 0. And after allocating this structure, the operating system sets the initial state of the thread to blocked. It puts just create a thread structure to some list called O list that I am going to explain later. In Pintos, there are 2 lists of processes or lists of threads. First one is ready list, and the second one is all list. Ready list is a set of threads that are ready for execution, and all list is a set of all threads in the system. So when the thread created, it is first inserted into the list called all list. And then all the threads that are ready for CPU execution are inserted into the ready list. Creating a thread, it first inserts the created thread structure to all list. And after putting it in all list, the operating system initializes the various fields in the thread structure and setting the state of the thread to ready list, and then put it in the ready list. In current Pintos operating system, whenever the operating system inserts the thread structure to the ready list or O list, it calls list under pushback under back. It means that operating system always places the just created thread at the very end of the list. Let me explain the function schedule. It is a very important function. Let me put 3 exclamation mark. It is a function which the operating system calls when it needs to schedule a new thread. New thread means scheduling a new thread means the operating system kicks out the currently running thread and then find the next thread to run and put it in the CPU. Then who calls schedule? The question is equivalent to saying that how the process releases CPU. There are 2 reasons. First one is voluntary release, and the other one is involuntary release. Involuntary release, the existing process calls exit, or it blocks, or it calls yield. Or in involuntary switch, the currently running process is involuntarily replaced with the other process. That happens when the higher priority process has arrived, or when the time quantum it has been using has expired. Before calling schedule, we have to disable interrupt, and then we have to change the states of a running thread from running to something else. Something else means that when a schedule is called in the block, and then the status goes to blocked. There are three reasons where the schedule is called: when the process exits, and when the process with an event or blocked, or when the process calls yield. So, in current Pintos operating system, there is no way for an operating system to switch out the existing process unless the process wants to. So in current Pintos operating system, there's no preemption. This is non-preemption. So in the course of doing the first project, we are going to turn this operating system into preemptive operating system. In preemptive operating system, Pintos, you are going to implement a scheduling module that kicks out the existing process if the newly incoming process has a higher priority. So this is actual code of Pintos. So this is a thread block. This thread block function is called when a thread asking for an IO completion. And then it calls a thread block, and inside thread block, it puts the state of the process in the thread blocked, and then it calls schedule. We are going to deal with the scheduling detail, so please bear with me for now. And then second topic is thread yield. When the running process wants to hands over the CPU to other process, then it calls yield. In yield, the currently running process puts itself to the end of the ready queue and hands over the existing CPU to the other process. So in that case, the existing process state becomes thread ready. And in third case, when the process exits, if the process exits, it changes states to thread dying, and then it calls schedule. This is the three situations where the schedule is called. Remember, in all these states, process voluntarily relinquish its CPU. Okay, so now let's look at the details of the schedule function. It gets the pointer to the current thread, and then it gets the pointer to the next thread to run. So this is where the scheduling discipline comes into play. So for example, you may want to use first come first served, or you want to use shortest job first, or you may want to use shortest time to completion algorithm, or you may want to use round robin. In all this scheduling algorithm, operating system selects what is the next thread to run. So in this next thread to run, operating system selects the next thread to run and returns the pointer to the just selected thread structure. After getting the pointers to the current running thread and the next thread to run, it calls a function called switch thread. So the function switch thread is responsible for saving the current context and restoring the next context of the next thread to run into the CPU registers. And it returns a pointer to the thread structure into the variable called PRV. After it is returned PRV, the operating system calls thread schedule tail, which puts the thread structure pointed by PREV at the end of the ready list. Now, I am going to explain the details of thread switch. As a first step, I'm going to explain what the stack is. Stack is a very primitive data structure. It contains an operation push and pop. And as you push the items to the stack top pointer grows. As you pop the data from the stack, the pointer grows the other end. So there's important register, we call it an ESP, a stack pointer, and it points to the top of the stack. And usually stack grows to the lower address space. Push ABC stores the value at the address pointed by ABC into the stack top and increases the stack pointer by 4. but increases the stack pointer by 4. Increasing the stack pointer by 4 corresponds to decreasing the ESP value by 4 byte. The next operation is pop ABC. It retrieves value which is pointed by the ESP pointer and saves it to the location pointed by ABC. And then it decreases the stack pointer by 4 byte. That is pop. So push and pop is the two basic operation in stack. Virtual address space of a process partitioned into two consecutive regions, user space and kernel space. In Pintos, virtual address space from 0 to 3 gigabytes forms a user space, and virtual address space beyond 3 gigabytes range forms a kernel address space. To access the kernel address space, the process needs to change its execution mode to the kernel mode. It is achieved by increasing its priority level. When the process runs in the user mode, it uses user stack to call the function and to define the local variables. When it switches the kernel and it executes in the kernel, it uses the kernel stack to access and use the function call. There's a kernel stack and there's user stack. I'm going to explain the detailed steps of switch thread. Switch thread function switches the two threads pointed by cur and next. Cur represents the currently running thread and next represents the next thread to run. It basically consists of 4 steps. First, it saves the registers to the kernel stack. And then it saves the location of the current stack top at the current thread's stack attribute. This one and this one. And then it restores the new thread stack top into CPU stack pointer. And then using the stack pointer just newly established, it restored the registers from the stack to the CPU. This represents the stack, current stack, and current stack top register value right after it calls switch thread. And there are 2 pointers, cur and next. It points to the thread structure of the currently running thread and the next thread to be run. And then there are 2 stacks. This is the kernel stack of current thread, and then this is the kernel stack of the next thread. And both of them are in the kernel stack, in kernel address region. And the stack pointer ESP points to the stack top of the current stack. This is the state of the memory layout right after switch thread is called. So it just jump to the switch thread function. And then after jumping into the switch thread, it stores the 4 CPU registers to the kernel stack of current threads. So after pushing EBX, EBP, ESI, and EDI registers, the stack pointer increases to the new stack top. To push 4 registers, the switch thread function executes 4 instructions, EBX, EBP, ESI, and EDI. So after executing these 4 instructions, it pushes the 4 registers of the currently running thread into the stack top, into the current kernel stack, and kernel stack is changes to point to the newly established stack top. After storing the 4 registers to the kernel stack, it's time to save the kernel stack top address to the thread structure of currently running thread. So in this figure, this stack attribute is set to point to the stack top of kernel stack. So it contains the stack top address of the ESP registers. The first thing it needs to do is to load the offset of stack attributes to the register EDX. Stack attributes is 24 bytes apart from the beginning of thread structure. So we first have to identify the amount of offset it has to jump from the beginning of the thread structure, and it is specified as this statement. And its macro thread underbar stack underbar offset represents the offset of stack attributes from the beginning of the thread structure. This is 24. So after executing this statement, edx becomes to contain the value 24. Next step is to load the beginning address of current struct thread to the EAX register. The next thing the operating system does is to save the location of current struct thread to EAX register. But how do we know the current location of current struct thread? If you look at the stack of the cur, and then there is a field CUR that saves the location of current thread structure, and it is from 20 byte apart from the ESP structure. So by switch cur, this represent 20, and then from stack pointer, if you go up for 20 byte, then that location contains the address of current struct thread data structure. So by executing this statement, the EAX register becomes contain the address of current thread structure. And then as a next step, we save the current thread stack type address to the struct thread stack field. So we move the value of ESP, the stack pointer, to this address, which is the EAX points to the beginning of the struct thread data structure, and EDX represents the offset between between the beginning of the thread structure until the location of the stack. And then there we save the value of ESP. And then as a result, let's go back to the few slides back. As a result, the pointer, the stack field, contains the address of the current stack top. And it looks like this. The next step is to switch the stack pointer points to the stack top of the next thread structure. Switching the stack top pointer from the stack top of the current thread to the stack top of the next thread consists of two steps basically. First one, it has to identify the location of the thread structure of the next thread. First, to do that, from this point goes up for 24 bytes and then identify the location of the next thread structure. And then after identifying the location of next thread structure, it identified offsets between the stack, between the beginning address of the thread structure till the stack resides. This is 24 byte. So after that, you can retrieve the location of the stack top pointer from here to the thread structure. Then the stack top pointer has successfully changed from the current thread to the new thread. If you look at the data structure, the first one to identify the location of the next thread structure is this instruction. So from stack top pointer, it goes up by 24 byte. This is the location of next thread structure. And then it contains the address of the thread structure of the next thread to run. That has been supplied by the caller to the switched thread. And then after loading the location of next thread structure to ECX, and then it adds the offset of stack field to this base location, and then it saves the address value located at that address to ESP. Then the ESP points to the new stack top, which is the stack top of the next thread. After switching the stack pointer to the new stack top, it pops 4 register values and then restore it to the 4 registers as EDI, ESI, EBP, and EBX. And then as a result of popping 4 register values, the stack top pointer is pointing has updated to this location. So it performs 4 pop instruction, and then kernel stack of the next thread is now updated as this. This is how we switch the 2 threads. After switching the current thread and the next thread, the next operating system updates the state of the newly selected thread as running. And if the previous thread was in the dying state, then operating system has to clear up all the pages allocated to that thread. So this is details of the code of thread schedule tail. So it updates the newly running thread as the thread running. And then if the color of the switch thread was in dying state, then it has to deallocate all the pages, allocate to the dying state process, and then freeze it. In this video, we have explained the details of context switch in Pintos operating system. Schedule function is called in exit, yield, and block, and it gets a new process to the CPU. There are 4 important steps in context switch. It saves the context of the currently running thread to the stack, and then save the current stack top at the currently running struct thread. And then it switches the stack top register pointing to the stack top of the next thread, and then it restores the context from the stack to the CPU. And after switching the 2 thread, it updates the state of the next running process and then frees the memory from the dying process.